Okay, in this video I'm going to try and quickly summarize topic 2.1 on DP physics, which is to do with motion. And what I've done here is a mind map with all the understandings that you need to know for 2.1 motion, which have been taken from the physics guide for 2016. So what do we start with? Distance and displacement. What is distance and what is displacement? Distance is the shortest distance between 2 points. And sometimes given the symbol little d. Whereas the displacement is the distance between 2 points in a certain direction. So it's given quantity s, and it's a vector quantity. So remember, vector quantities have both a magnitude and a direction. Similarly, speed is just defined as the distance travelled over the total time taken. Distance over time, and it's in meters per second. Whereas velocity is the change in displacement over the change in time. Also in meters per second, but it has both a size and a magnitude, so it's a vector quantity. And we often give a velocity the symbol little v. As regards acceleration, it's defined as the the rate of change of velocity. And we can either work out an average acceleration, which is change velocity over change in time, or we can work out the instantaneous acceleration, which you can only really define or calculate as the gradient of a tangent to the velocity time graph. We're going to come on to the graphs of motion in just a second. In terms of the graphs of motion, what graphs of motion are we talking about? Well, there's three graphs of motion. We have, now I'm only going to be talking about the vector quantities. We have the displacement time graph, ST graph. We have the velocity time graph, VT graph. And we have the acceleration time graph. Now it's important to know how to interpret these graphs and the meaning of the gradient and the area under the graphs in each case. So if I do a little table below here, so we might have, let's take an example, let's have an ST graph that looks like this. Now because the meaning of the gradient of the ST graph is the velocity, because we have a linear ST graph, we have a constant acceleration, therefore the rate of change of displacement is constant, so we have a constant velocity and a zero acceleration. So the meaning of the gradient of the ST graph is the velocity. The area under the ST graph has no meaning. The meaning of the gradient of the VT graph is the acceleration. And the area under the VT graph is the change in displacement, delta S. The meaning of the AT graph, the meaning of the gradient of the AT graph has no meaning in this context, but the meaning of the area under the AT graph is the change in velocity, delta V. So this is what the graphs of motion would look like for uniform motion, where there's no acceleration. However, if I just rub out these graphs here, if I was to have a uniform accelerated motion, for example, an object moving under free fall in the presence of gravity, the displacement time graph will be a curve, no longer be a straight line. The velocity time graph will be a straight line, and the acceleration time graph would be a straight line. So that's how you would interpret the graphs of motion. Now you might also have a case where you have non-uniform acceleration, in which case the ST graph might look like this. It might start off as a curve, but then it might become linear, in which case we would have a positive velocity in the beginning, or we would have a change in velocity in the beginning going from 0 to a positive value, reaching some terminal velocity. Here coming on to the concepts of fluid resistance and terminal speed. And here, if we look at the rate of change of velocity, it's not constant with time, so we'd start with having a positive acceleration, but then as the rate of change of velocity decreases, the acceleration time graph would reach a zero value at a certain time. However, let's just delete those three graphs there. That was non-uniform acceleration. Let's go back to the case when we had uniform acceleration. So for example, free fall due to gravity. That would be the three graphs given there. If we have uniform acceleration, then we're given a number of formulae which we can use, and these are in the data booklet. And there's a data booklet reference in the guide. So the four formulae you're given, which you can use only during uniform acceleration, are v equals u plus at, s equals ut plus a half at squared, v squared equals u squared plus 2as, and s equals v plus u divided by 2 times by t. In this context, u is the initial velocity, and t is the change in time, the difference in time between the initial and the final velocity. V is the final velocity. Coming on then to projectile motion, if close to the Earth I launch a projectile and the horizontal velocity is non-zero, then basically the path of the projectile will follow a parabola like this, and by resolving the velocity into components, we can basically see that for projectile motion we have uniform velocity in the x direction, but we have uniform acceleration in the y direction. So you have to treat the x and the y directions independently and use the equations for uniform motion in the x and the equations for uniform acceleration in the y directions. You're not given any extra equations other than this, but it's good to know that you might have to resolve into components, and also that remember that if we launch a projectile at an angle theta to the horizontal with an initial velocity v, then the horizontal component will be v cosine theta, and the vertical component will be v sine theta. Now, as regards fluid resistance, for small heavy objects falling in air, then we don't have to take fluid resistance into account. But as soon as we have a large light object falling in air, or we have something falling in a viscous fluid, we have to take fluid resistance into account. That means that as this is the object here, as it's falling, it's always going to have a force of gravity on it, mg, acting downwards, which is going to be constant. But as the velocity increases, so here we drop it from rest, as the velocity increases, the resistive force is also going to increase. Here it starts, well, there's no resistive force in the beginning. Then as it starts moving, the resistive force increases, and at some speed the fluid resistance force is going to equal the force due to gravity, and we're going to have terminal speed. We're going to arrive at terminal speed, which is given sometimes given the symbol v subscript t.